Hello, today we're continuing with our GCSE Physics Revision series looking at hydraulics. And let me draw you a typical hydraulic system. These are essentially pipes in which we put a fluid. It could be water, although usually it's some form of oil that is used. And we put what's called pistons at the surface of the fluid. The point about pistons is they do not allow the fluid to seep through. So if you push down on this piston, that fluid, that piston will go down and it will push the fluid down and it will push this piston up. And what we're relying on here is that liquids are largely incompressible. That means you cannot squash liquids to a smaller state. If you fill a balloon with water, you can change its shape, okay, by just squashing it, but you cannot reduce the overall volume of water because that water is what's called incompressible. Consequently, if you push down on this piston here, causing the piston to go down, then what will happen is that the volume of water cannot decrease. Consequently, that will cause this piston to go up. Now, here's the important point about pushing liquids. If you push on a liquid, you create pressure. And yet again, pressure has the letter P. So P is not power, and it's not momentum in this case, it's pressure. And when you push on a liquid with a certain pressure, that pressure is transmitted through the liquid in all directions. So if I apply a pressure P to the piston, there will be a pressure in the liquid, and that pressure will apply in all directions on all surfaces. Whichever way you look, that pressure P will apply. Now, what is that pressure? We haven't dealt with pressures so far, we've talked about forces. And there's a very good relationship between pressure and force. Pressure is equal to the force you apply divided by the area over which you apply it. So this piston will have a certain surface area, and we therefore press down on it with a force, and the force divided by the area tells you what the pressure is. And that pressure is transmitted throughout the fluid. That pressure presses on everything, including the piston here. So let's just redraw that diagram, because we're going to need to see something rather interesting that's going to happen as a consequence. You can see from the way that I've drawn it that the area of this piston, which we'll call A1, is very much less than the area of this piston, which we're going to call A2. And now I'm going to assume that I press down on this piston with a force F1, and that is going to be transmitted through the fluid. This is all fluid in here. That is going to be transmitted through the fluid, the pressure is, until you get here, and that is going to result in a force F2 here. But the pressures are the same. Now the pressure, as we just said, here is F1 over A1. But that pressure is transmitted through the fluid in all directions, including pushing up. The pressure pushing up on this piston is the same as the pressure pushing down on this system, because the pressure is transmitted. And so the pressure here is also going to be force over area. In this case, force F2 over area A2. Right? Pressure cannot be lost. Pressure is transmitted through the fluid in all directions. So pressure is force over area. I push down on this piston with force F1. The area of the piston is A1. That produces a pressure F1 over A1. That pressure is transmitted all the way through the fluid until it gets to this piston. That piston is subjected to the same pressure. And so that pressure is going to be the force acting upwards divided by the area F2 over A2. Now let's suppose that the area here is 1 metre squared. And let's suppose that the area here is 10 metres squared. So the area here is 10 times the area here. And let's suppose I press down with a force of 10 newtons. Consequently, what we can say from this here is that I want to know what F2 is. F2, if we rearrange this formula, is going to be F1 over A1 times A2. F2 is F1 over A1, and then you bring the A2 up that side. F2 is F1 over A1 times A2. So F2, which I don't know, is F1, well, I told you that was 10 newtons. 10 newtons, and A1 is 1 metre squared, so it's 10 divided by 1 times A2. Well, A2, I told you, was 10 metres squared. So it's times 10. And that's 100 newtons. And this sounds like a free lunch. Look what's happened. I have pushed down on this small piston with a force of 10 newtons. The pressure has been transmitted through the fluid, and I have got, on an area of 10 metres squared, a force of 100 newtons. I only exerted 10 newtons, but what I get back is 100 newtons of force. This is a typical hydraulic system. You could have a system, if you built it well enough, where if you have a very small area that side, but, whoops, I overdid that a bit there, but a very large area this side, you could have a situation where you push down on the piston this side, and you could make a car go up in the air on that side. A small force on this side produces a huge force on this side, because the pressure remains the same, and pressure is force over area. And that's how hydraulic systems are used. You apply a small force onto a small area, the pressure is transmitted through the liquid, and you get a much larger force at the other side because you've got a larger area. That sounds like a free lunch. Where's the catch? Well, think about it. That liquid, we've said, is incompressible. That's the whole point. That's why pressure is transmitted through the fluid. Now think about the volumes of the fluid concerned. Suppose I push down by 1 metre. I'm not going to actually push down very, very much fluid, because this is a very, very thin pipe. So the total volume here is quite small. Consequently, the volume by which this will rise will be quite small, given that the area is so large. So in fact, the car is only going to move up maybe by 10 centimetres. So the catch is that although I only have to apply a small force, I have to apply it over a much larger distance, because the large force at this side will only go up by a small distance. And you'll remember that we showed that the work done, which is energy, is force times distance. And that is conserved. That is the point. That a small force acting over a large distance produces a large force acting over a small distance. Small f times large D is equal to large F times small d. The point is that if you want that car to go high up on a ramp, you're going to have to push this down an awful long way, because it doesn't go up metre for metre. the work done is force times distance, and that will be the same on both sides. So the force that you push down on that side times the distance you travel on that side will equal the force up on that side times the distance up on that side. And since you've got a much smaller force on this side, you're going to have a much smaller distance on this side. So let's just do one more calculation of this system. Here is the thin side, here is the thick side, there's the two pistons, the whole thing is filled with liquid. I push down with a force of 10 newtons, and the area, let's say here, is 0.1 meter squared, and this area is going to be, say, 2 meters squared. Firstly, I want to know what this force is, which we'll call F2. And secondly, if I push down by 1 meter, how far up will that piston rise? Well, the first thing we need to do is to find out what F2 is. We know that the pressure is force over area, so the pressure is going to be force, which is 10 newtons, divided by area, which is 0.1 meters squared, and that's going to be 100 newtons. Sorry, 100, not newtons. The unit of pressure is called pascal, or if you like, newtons per square meter. Newtons per square meter, because this is force in newtons divided by area, which is in meters squared. So it's newtons per square meter, but it's actually given the name for pressure of pascal. So it's 100 pascal, and that pressure is transmitted here and becomes force over area here. So now we know that the area is 2 meters squared, so we know that the pressure, which is 100 pascals, is equal to the force, which is F2, divided by the area, which is 2. That means that F2 equals 200 newtons. So I press down with a force of 10 newtons, but my prize is an upward force of 200 newtons. 20 times as large. But the second part of the question was, if I push down over a meter, how far up does this go? And you'll remember that work is the same on both sides, and work is force times distance. On this side, I've got a force of 10 newtons travelling through a distance of 1 metre. So on the left-hand side, that work is going to be 10 newtons times 1 metre, which is 10 joules, because work is a measure of energy. And the same work is therefore done on this side. So on this side, the work is going to be, again, force times distance. We know that the force is 200 newtons, because we calculated that, times the distance. That is going to equal 10 joules, which means the distance is going to be 10 divided by 200 meters, which is 0.05 meters, or if you prefer, 5 centimeters. So actually, you had to push down a whole meter in order to get this side to rise by just 5 centimeters. So you can see what's happening. You're getting a very large force compared to the one you've exerted, but it doesn't travel up so far, and you'd have to push down a long way if you wanted to get a significant lift. Nonetheless, hydraulics can take a small force and amplify it to a larger force, but as I said, the price is that the small force has to travel over a much larger distance than the larger force will.